Now let's talk about reflection in the x-axis symbolically. Recall that if I plot the point AB, its reflection in the x-axis is the point A, negative B. So the y-coordinate is changing this time, and the x-coordinate is staying the same. In order to do that with a function and symbolic notation, recall that y equals f of x. So if y is changing, we need to change y, negative y. But since y equals f of x, we're really looking at negative f of x. Notice how this is different than the y-axis reflection, f of negative x. Notice where the negative is. Negative on the inside, we're reflecting over the y-axis. Negative on the outside, we're reflecting over the x-axis. So let's try this again. We'll use the same function as before, x plus 1. And this time we'll look at reflecting across the x-axis, which means we change the y-coordinate, negative f of x. We're not plugging anything in this time like before. We're not replacing the x with a negative. We're putting a negative in front of the whole function. Simplifying this out, we get negative x minus 1, and we're going to call this new function g of x, or h, or whatever you want to. Call it something different. And sure enough, you can see that that's how we have it here. Notice the use of parentheses when we multiply, when we're applying this negative 1. The negative needs to apply to everything in that function's symbolic representation. So all the signs get changed. Similarly, looking at the graph, we can see 3 significant points here on the graph of f, and its reflection across the x-axis gives us our new graph g. And also notice here negative 1, 0, and 1. We get our reflections for points across the x-axis. Let's play the same game we played before. We're reflecting the x-axis this time. We're going to change the symbols, make a table, and then graph. So let's take a look at number 5 together. F of x equals 2x minus 1. To change our graph symbolically, reflecting across the x-axis this time, we're going to negate the entire function. Make the y-coordinate negative. Remember that f of x and y mean the same thing. Multiplying this out, distribute that negative sign. Negative 2x plus 1 is our new function g, reflected across the x-axis. Making a table, we already have some points here for our function f. I'm going to pick off a couple. We can look at 0, 1, and 2. Plugging in 0 to f, we get negative 1. Plugging in 1, 2 times 1 minus 1 will give us 1. And plugging in 2, 4 minus 1 will give us 3. What should happen for g is these numbers should be opposite. So let's check it. G of 0, negative 2 times 0 plus 1, positive 1. G of 1, negative 2 times 1 plus 1, negative 2 plus 1 is negative 1. And then G of 2, negative 2 times 2 plus 1, negative 4 plus 1, negative 3. Now plotting these ordered pairs, connecting the dots, we have our reflection across the x-axis. Try these next two on your own, pause the video, and when you resume, check your work. Now looking at problems 6 and 7, notice we negate the entire expression, so g of x is negative x minus 1 squared, and we're reflecting that graph across the x-axis. Similarly for number 7, f of x is x to the third. We apply the negative to negate the expression, and we get g of x is negative x to the third. What makes this one really interesting is that reflecting across the x-axis and reflecting across the y-axis give us exactly the same function, which is kind of cool. Let's work through number 8. Negative f of x, negative 1 over x. That'll be our g function. And we end up with, exactly like the previous one, reflection across the x-axis lends to the exact same function as reflection across the y-axis does. Number 9 is definitely different. negating the whole function, negative quantity x squared plus 1. We're going to get negative x squared minus 1 for our new function. We're just distributing that negative sign. And make your table, and you should get a reflected parabola that looks like that one. Now let's reverse things and see if we can identify that type of reflection again. Here we have a symbolic representation of our function f. Its reflection g, and we need to determine what type of reflection is happening. So in this case, we can guess and check. There's nothing wrong with that method. We only have two different ways to change our function for reflections. We either plug in a negative x, or we negate the whole expression. So we can try that for each of these functions f and see which one matches the reflected function g. I'll make my table pretty big. I'll get some color codes going in here. So y-axis reflection will be in green. X-axis reflection will be in purple. So we'll start out with the y-axis reflection. Y means change x. So I'll plug in negative x into my function. I'll simplify it in a minute. For the x-axis reflection, we have negative on the outside. And if I simplify these, negative 3x plus 1 for our y-axis reflection, for our x-axis reflection, negative 3x minus 1. But I notice that the negative 3x plus 1 matches my reflected function. So this is a y-axis reflection. Reflection across the y-axis. The only thing that changes sign is the x term, not the whole function. So changing the sign on the x term means we plugged in a negative x to get that change. Take a look at the next one. F of negative x means we're going to plug in a negative x squared minus 2. Negative x squared is just going to be x squared minus 2. If I do an x-axis reflection, negative f of x, negative everything, distribute the negative, negative x squared plus 2, and I see that this x-axis reflection matches the reflected function. So this is an x-axis reflection. And then for the last one, which is a little complicated, but we can get through it, f of negative x, I'm going to replace the x with a negative and try to simplify it. If I'm doing an x-axis reflection, negative f of x, negate the whole thing, x cubed plus 1 over x squared. Let's do the y-axis reflection, negative x to the third. The negative to the third, negative times negative times negative. We can look at this as negative 1. Negative 1 times negative 1 times negative 1 gives us a negative 1. And then x to the third will just stay as x to the third. Over here in the 1 over negative x squared, negative x times negative x, the negatives turn positive. So we're left with x squared. In our x-axis reflection, we're just distributing that negative to both of these terms. So we end up with negative x to the third minus 1 over x squared. And if I look at these two and compare them to my reflected function g, the one that matches is my y-axis reflection. And then the last part of our lesson is, again, something I'm not going to test you on. That's an optional section on double reflection. This time we're going to look at x-axis and y-axis reflection, a double reflection, reflection in both. In order to do this symbolically, we're going to negate the whole function and plug in a negative. We do both of them. So we can do that for these graphs. One thing that I do want to point out is down here, if I reflect across the x and across the y, negative 1 over negative x, the negatives are going to cancel and I get the same function. What makes this super important is that this function, 1 over x, is symmetric with respect to the origin. It has symmetry in the double reflection. So if I fold my paper along the y-axis and along the x-axis, these two pieces of the same function will land on top of each other. So we have this symmetric with respect to the origin. And there's another one that's symmetric with respect to the origin. And I'm going to let this last question be a little bit of a bonus extra credit for you. In your weekly wrap-up, if you can identify which function that is symmetric with respect to the origin, just write it in your summary and it'll be worth a bonus point. One of those rare moments where I have an inspiration of additional extra credit beyond what I'm already giving you with the Smart Shops. So try it out. See if you can identify that other function that's also symmetric with respect to the origin. Remember, I'm not going to be testing you on double reflections. Reflecting once is good. Being able to reflect across the x or across the y, those are important.